It's recorded history now, the exploration and discovery of oil and gas in lands beneath the sea. The giant drilling platforms that grew like mushrooms out of the water, searching for the products so important to a world that runs on oil. Men and machines laying underwater pipelines to carry crude oil and natural gas. Pipelines that stretch out like life-giving arteries from a pumping heart to processing locations on shore. Pipelines that today can truly be regarded as lifelines tomorrow. The beginning of the offshore industry can be traced to the coastal region of the state of Louisiana, along the Gulf of Mexico, where millions and millions of acres of marsh confuse the distinction between land and sea. For thousands of years, the earth in this area struggled to rise above the waters, and man's only association here was for trapping and fishing. But in the mid-1930s, the petroleum industry, faced with depleting oil deposits on the mainland, began to contemplate the shallow bays, lakes, bayous, and marshes. Though the odds were against setting up drilling equipment in such an environment, hard work and determination saw the industry eventually established among the sawgrass and wild rice. Petroleum engineers found that submersible drilling apparatus could be used in the shallows, where the water was deep enough to float the heavy equipment. And by 1937, our company, J. Ray McDermott, was building fixed platforms over marshy areas for the industry. But wildcat sites far from solid land presented many problems. Problems that challenged our company's engineers. Bored roadways to the locations often sank out of sight from their own weight. So we built them on pilings. And laying pipelines across a slough was almost impossible. So one day in 1938, a group of our men walked an ordinary dragline onto a small barge, then dug through the marsh, creating the first pipeline canal ever prepared from floating equipment. The barge-mounted draglines opened up the swamps and marshlands to wildcatters, and there the industry flourished for a while. By 1947, exploring the deeper waters into the Gulf of Mexico had begun, and several wood-piled platforms dotted the waters. A new offshore industry was born. But the growth was slow, and sometimes painful, discouraging, and costly. However, as discoveries of rich petroleum deposits were made farther and farther from the shore, the industry courageously moved to deeper and deeper water. But wooden structures were impractical there. So our company designed the first steel template-type platforms and set them in 20 feet of water. By 1948, we had successfully placed similar structures in water depths up to 50 feet. The offshore industry was on its way, and so were we. In 1949, we built our first derrick barge, specifically designed for offshore work. It had a lifting capacity of 150 tons. 4 years later, we commissioned a second unit. Its capacity was 250 tons, which allowed us to work with bigger structures. And by 1955, we were setting jackets in water depths of 100 feet. We set a record in 1959 by installing a platform in water 204 feet deep. By this time, underwater pipelines were recognized as the most reliable means of getting the oil and natural gas to land-based terminals. So we built specialized pipelaying equipment, modified a derrick barge to accommodate it, and became the pioneers of the marine pipeline industry. As pipelaying became more and more a full-time business, we began permanent conversion of some of our derrick barges. By 1961, we had begun the construction of barges designed specifically for pipelaying. The new specialized barges permitted rapid pipeline assembly, and in 1962, we laid the longest marine pipeline in the United States. By 1963, we had added another new pipe-laying barge to our growing flotilla. It was big enough to accommodate 100 workers and was designed to handle 18-inch diameter pipe. During the next 4 years, we established and broke many records for underwater pipelines. By the end of 1967, we had amassed one of the world's largest ocean-going fleets of heavy construction equipment. Open water drilling had spread to other parts of the world. We were called on to service the petroleum industry in the Middle East, off the Nigerian and Gabon coasts, the Gulf of Suez, Cook Inlet of Alaska, Australia, in the Pacific off California, the Bahamas, and in the North Sea. Marine pipeline technology was beginning to take great strides, and as pipe-laying requirements became more complex, we knew that bigger lay barges would be needed. In late 1969, we placed into service two of the largest and most modern pipe-laying barges in the world. Each vessel, 1.5 times as long as a football field, was designed to meet the requirements of laying large diameter pipe in deep, rough water. The remaining frontiers in the search for tomorrow's energy would create little challenge to these giants.
Working aboard a floating offshore assembly line this size are as many as 220 tradesmen and technicians. Welders, X-ray technicians, riggers, crane operators, line-up station operators, divers, field engineers, and many others. 30 barge crewmen support and operate the onboard facilities. Towermen, tug captains, laundrymen, marine engineers, maintenance men, cooks, and bakers, all necessary for around-the-clock support of the barge. Powerless alone, the barge must be towed to sea, and once in position, it is stabilized by 12 anchors. 2 100-ton gantry cranes, 6 electronically controlled davits, a control tower, and assembly line shelters make up the major deck equipment and facilities. The pipe assembly line is located in the center of the barge. This design affords stability, safety, and a centralized work position. Pipe sizes up to 48 inches in diameter can be handled. A cargo barge supplies the pipe. Each section, called a joint, is 40 feet long and has a concrete coating which provides the weight necessary to sink the pipeline. The concrete coating, sometimes as thick as 3 1/4 inches, also affords protection against the corroding seawater. Before going to the assembly line, each pipe section is buffed and cleaned to remove any scale or rust which may have accumulated. With the required heading for the pipeline, established by an electronic surveying device, the assembly work begins. At the first of 5 welding stations, the beginning sections are hoisted onto the line and moved into position. An internal line-up device assists in aligning each successive joint before welding begins. Nothing short of a near-perfect fit will pass inspection. The first welding pass, which joins the pipes, is followed by a hot pass over the same area to add strength before the line is moved to the next station. Large diameter pipe permits visual inspection of the inside seam. Welding corrections can be made before the seam reaches the last station, thus eliminating production downtime. As the pipe moves through the succeeding stations, welders fill the seam to the thickness of the pipe wall. Then at the final welding station, the seam is capped. "100% X-ray inspection of each seam erases any doubt that the weld is top quality. Moving along to the next station, the welded area receives a protective waterproof coating. At the last assembly station, a sheet metal form is fitted around the coated area. Cement or other approved field joint material is poured into the form, providing a continuous protective coating over the pipe joint. With the assembly line method of joining pipe section to pipe section underway, the line moves off the stern of the barge and down to the ocean floor by means of a device known as a stinger. The stinger, extending from the stern, acts as a conveyor which gently carries the pipeline on its way to the floor. By controlling its buoyancy, the stinger can be adjusted to the required shape for the water depth, pipe size, and weight. Controlled tension, regulated by electronic sensors, is applied to the pipeline to further relieve stress on the line during its descent. As soon as the first section of the line has reached the floor, the barge begins its forward movement, 40 feet at a time, as each new pipe section is placed in the lineup station. This movement is accomplished by simultaneously taking in anchor lines at the bow while letting out lines at the stern. As an operational aid, closed-circuit television is used to observe all 12 anchor winches during the forward movement. Reaching forward up to 5,000 feet are 6 20,000-pound anchors. The same number are extended from the stern. In order to maintain an almost constant forward movement of the lay barge, tugs are continually moving anchors, farther away at the bow and closer in at the stern. This assures that there will always be enough anchors firmly embedded in the seafloor to provide a steady working attitude, while at the same time allowing the barge to move forward when required. Sometimes the buoys that mark the anchor locations come in handy for a tired traveler. As the barge winches forward, surveillance is kept on the welding station so that precise positioning of the line on the barge can be attained. The routine continues day and night as long as the weather holds. Scheduled visual inspections of the line riding through the Stinger provide assurance that all is going well. The end of a work shift finds the pipeliners below deck in the comfort of recreation rooms, lounges,
Ladies and gentlemen, the Partridge Family.
the movie theater,
Can't have everything, big boy.
or the dining room.
It was sort of watching the Redskins.
Watching the Redskins. Did he watch the Saints game?
No.
That was a good game.
Pass the butter, will you, Henry?
Because pipelaying is a 24-hour day operation, all support must be continuous and well coordinated. A constant movement of helicopters, supply vessels, tugs, and crew boats keeps men, supplies, and equipment in the right places at the right times. Support for the huge lay barges is conducted from shore-based headquarters. Here, a constant watch is kept on pipelaying progress.
When you want your gal and the engineer crew tomorrow morning?
Supplies are coordinated. Special fabricating jobs, such as risers, underwater valve assemblies, scraper traps, and interconnecting pipe are handled. Welders are qualified. Safety regulations established. And engineering problems solved.
20 miles or 18 inch.
That's all
All
right
gonna
here.
start, right,
First,
right. We're gonna start the 30 inch from 509 and up in this particular block. 565.
Bringing the underwater pipeline to the surface to make connections at platforms along the route is not an assembly line operation and must be done when the seas are relatively calm. The lay barge is positioned next to the structure and parallel to the pipeline lying on the seafloor. Attaching the riser section is done at deck level, which means that the end of the pipeline must be raised out of the water. Davits located on the starboard side of the barge are used for the lift. Divers secure the hoisting cables around the pipeline and provide visual surveillance during its ascent.
How deep is it under the pipe now?
Right where I am, it's about a foot.
Tension is applied to the lifting cables. Davits and cables are checked and rechecked. Now, automation takes over the lift. Controlled by electronic sensors, which govern the rate that each davit will hoist its cable, the system assures an even lift on the pipeline, thus effecting an evenly distributed weight and preventing unnecessary stress. With almost no discernible movement, the davits take up cable and the pipeline begins its ascent. Night falls, as it does many times before a pipeline is finished. But the work goes on. Finally, the end of the pipe emerges from the water and is secured at deck level. The end cap is cut off and the pipe prepared to receive the riser. The hugeness of the barge minimizes wave movement while welders join the two sections. With the riser now an integral part of the pipeline, it is lowered and more lengths of the pipe are added, enough to clear the water when it again rests on the sea floor. Securing the line to the platform completes the underwater phase of the riser installation. The barge prepares to move to another location and another pipeline.
What we would have given for a lay barge like that back in the 50s. Marine pipeline equipment sure has come a long way. In 1958, we were using a modified ditch digger to bury pipelines in 70 feet of water. Nowadays, we bury pipe with big jet barges like this one. Huge compressors on deck supply high-pressure air and water to a sled which can operate down to 500 feet. The sled straddles the pipe after it has been laid. Then, while being pulled by the barge, directs high-pressure air and water jets to blast a trench under the pipe. After the pipe settles into the protective trench, natural soil movement covers it over. Another very sophisticated piece of equipment which advances the state of the art from science fiction to reality is this mammoth subsea pipeline alignment frame. It was designed and built by our company to provide a dry, lighted environment around a pipeline down to depths of 800 feet. It can be used for repair work or installing side taps on a line. Who would have imagined equipment like this when the industry moved offshore in the 40s? Yet during those early years, much of the progress and development could be attributed to imagination. Without the courage, determination, and vision of the men who pioneered the industry, it still might be floundering in the marshes. In this big frontier where the search for energy continues, and the equipment to get it out and sent to shore becomes more complex and scientific, imagination and inventiveness are still two very important ingredients. We've come a long way since our early years. And each year, the pace quickens. Bigger pipelines, more distant fields, deeper waters. Keep the oil and gas flowing. Get the energy ashore. And as time goes on, today's pipeline becomes tomorrow's lifeline.